Imagine the universe in its very first seconds, a searing, dense soup of particles and energy, hotter and brighter than any star that would ever exist. In that primordial fire where matter and energy were one, something extraordinary happened. A ghost was born, not a ghost from folklore, but a cosmic one, a particle so elusive it can pass through an entire planet without ever bumping into a single atom. These are neutrinos, and they are everywhere. Billions are streaming through your body at this very moment, silent and undetected, a whisper from the dawn of time. They are the universe's most untold story, and today we are going to listen. This ancient light, the cosmic neutrino background, is a snapshot frozen in time from just 1 second after the Big Bang. It is the oldest fossil in the cosmos, even older than the famous cosmic microwave background. Yet, for all its age and abundance, it holds secrets that have baffled scientists for decades. We are surrounded by these relics, bathed in an ocean of these ghostly particles, and yet we understand so little about them. How did they shape the cosmos? What can they tell us about the birth of galaxies, the nature of dark matter, or the very fate of our universe? These are not just academic questions, they are the keys to unlocking the deepest mysteries of our existence. In this journey, we will become cosmic detectives, uncovering 25 profound mysteries surrounding the cosmic neutrino background. From their impossible lightness to their role in the universe's largest structures, each mystery pulls us deeper into a story more incredible than any work of fiction. This is a tale of persistence, of brilliant minds trying to catch a shadow, and of a universe that is far stranger and more wonderful than we ever imagined. So join me as we step into the unknown, tracing the faintest echoes of creation to answer the biggest questions we can possibly ask. To truly appreciate our first mystery, we have to rewind the cosmic clock all the way back to the very beginning. Picture the universe in its infancy, not even a full second old. It is an unimaginably hot, dense, and chaotic place, a plasma so intense that light itself is trapped, bouncing endlessly between particles. In this primordial cauldron, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were once unified as a single super force. But as the universe expanded and cooled at a ferocious rate, these forces began to separate in a process physicists call symmetry breaking. The first to peel away was gravity. Then, just 1 second after the moment of creation, something pivotal occurred. The weak nuclear force which governs radioactive decay finally decoupled from the electromagnetic force. This monumental event had a profound consequence. It set the neutrinos free. In that instant, these ghostly particles stopped interacting with the hot soup of plasma and began streaming across the universe unimpeded and unchanging. This is the birth of the cosmic neutrino background. To put its age into perspective, the more famous cosmic microwave background, the afterglow of the Big Bang that we often see depicted as a map of the cosmos, didn't form until about 380,000 years later. That means the neutrino background is the oldest known fossil in the entire universe, a snapshot from its very first breath. These ancient neutrinos have been traveling for almost 14 billion years, and they are all around us, a silent echo of that initial moment of separation. This leads us directly to the heart of the mystery. If these relic neutrinos are so ancient and so abundant, billions passing through you every second, why have we never directly detected them? The answer lies in their ghostly nature. Neutrinos are elemental ghosts. They are neutral, meaning they carry no electrical charge, and they interact only via the weak nuclear force and gravity. This makes them incredibly aloof. The weak force has such a short range that for a neutrino to bump into another particle, it has to hit an atomic nucleus almost perfectly head-on. The overwhelming majority of them simply pass right through. In fact, a neutrino could travel through a light year of lead, a solid wall of metal over 6 trillion miles thick, and still have a good chance of making it out the other side unscathed. This presents an almost insurmountable challenge for scientists. How do you build a detector for something that refuses to interact with anything? Our current detectors, like the massive Super Kamiok and in Japan or the Ice Cube Neutrino Observatory in Antarctica, are engineering marvels. They use enormous volumes of ultra-pure water or ice to wait for that 1 in a trillion chance that a higher energy neutrino from the sun or a distant supernova will actually collide with an atom and create a tiny flash of light. But the neutrinos from the cosmic background are different. They have been traveling for eons, and the expansion of the universe has stretched their wavelengths and sapped their energy to an astonishingly low level. They are now incredibly cold and slow-moving, with energies millions of times weaker than even the neutrinos we struggle to detect from our own sun. Catching one of these ancient, ultra-low-energy ghosts would be like trying to hear a single, specific pin drop in a hurricane happening on another planet. Our technology simply isn't sensitive enough yet. We are surrounded by the oldest particles in existence, bathing in a sea of cosmic history, and yet they remain just beyond our grasp, the universe's most profound and silent secret. This profound inability to directly detect the oldest neutrinos in the universe leads us directly to our second, and perhaps even more perplexing, mystery, the case of the missing neutrinos. We know the cosmic neutrino background must exist. Our most robust theories of the Big Bang, supported by a mountain of evidence, insist upon it. We can even calculate with a high degree of confidence just how many of these relic neutrinos should be in every cubic centimeter of space. The number is staggering. Scientists estimate there should be about 336 of these ancient particles in every single cubic centimeter of the universe. That means the space in a single sugar cube, if we could somehow isolate it, should contain hundreds of them. And yet, when we add up all the neutrinos we can actually detect from all known sources, the sun, supernova, nuclear reactors, even the Earth itself, the total number falls dramatically short of that predicted vast sea of primordial neutrinos. A huge portion of the universe's most abundant particle is simply unaccounted for. This is the missing neutrinos paradox, and it hints that our understanding of the cosmos might have a fundamental flaw. So where did they all go? Cosmologists and particle physicists have proposed several compelling and some wildly exotic explanations for this discrepancy. The first possibility is that we are simply looking for them the wrong way. Our detectors are finely tuned to catch neutrinos with specific higher energies, like those generated in stellar furnaces. The Big Bang neutrinos, by contrast, have had their energy redshifted by the expansion of the universe to almost nothing. They are ultra-cold, moving at a fraction of the speed of light. It's possible they are so feeble that they interact in ways we haven't even begun to imagine, slipping through our nets not because they aren't there, but because our nets are designed for bigger fish. We may need an entirely new class of detector, one capable of sensing these incredibly subtle whispers. Another fascinating theory suggests that these relic neutrinos might not be stable over trillions of years. What if they aren't missing but have simply decayed? We know that many particles have a finite lifespan, transforming into lighter, less interactive particles over time. If neutrinos have even a tiny tendency to decay, the vast majority of those born in the first second might have already vanished, leaving behind only a faint trace of their original population. This would force us to rewrite the standard model of particle physics, introducing new properties for a particle we are still struggling to understand. The most mind-bending possibility, however, is that the paradox points to an error in our basic story of the universe's birth. Our prediction of 336 neutrinos per cubic centimeter relies on our precise model of the Big Bang and the subsequent formation of the elements. The early universe was like a cosmic nuclear reactor, and the amount of hydrogen and helium it produced is exquisitely sensitive to the number of different types of lightweight particles, like neutrinos, that were present and freely streaming around at the time. The observed abundance of these primordial elements matches our predictions almost perfectly, but only if we assume the standard 3 types or flavors of neutrinos. If there were more types of lightweight particles present in that early soup, perhaps a theoretical 4th, sterile neutrino that interacts only through gravity, it would have altered the nuclear fusion recipe and left a different elemental fingerprint. The fact that the elements match the 3 neutrino prediction suggests the sterile neutrino wasn't there, deepening the mystery of where the particles we expect actually are. This paradox forces us to question everything from the fundamental nature of particles to the very conditions of the universe's first moment, making it one of the most significant unsolved problems at the intersection of cosmology and particle physics. But this ghostly nature and our struggle to detect them is only the beginning of the puzzle. To unlock the deeper secrets held by these ancient particles, we must confront one of the most fundamental and stubborn questions in all of modern physics. What do neutrinos actually weigh? We know they have mass, but we don't know the order of their masses. This is known as the neutrino mass hierarchy conundrum, and it's a problem the Cosmic Neutrino Background is uniquely positioned to solve. Imagine you have 3 identical-looking boxes, and you know they all have different weights, but you can't tell which is the lightest and which is the heaviest just by holding them. This is precisely where we are with the 3 known types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Through ingenious experiments, we've discovered that neutrinos can oscillate or change from one flavor into another as they travel. This strange quantum phenomenon is only possible if they have mass, but it only tells us the differences between their masses, not the actual order. We have the relative weights, but we don't know the final ranking. There are 2 possible scenarios for this mass ordering. In the normal hierarchy, the 2 lightest neutrinos are very close in mass, and the third is significantly heavier, much like a family with 2 children who weigh almost the same and one parent who is heavier. The inverted hierarchy flips this script entirely. Here, the 2 heaviest neutrinos are very close in mass, and the third one is the lightest. It would be like that same family having 2 parents of nearly identical weight and one very light child. Our most powerful particle accelerators and underground detectors have been trying to distinguish between these 2 possibilities for years, but the results remain tantalizingly inconclusive. The differences are so subtle that they lie just at the edge of our experimental capabilities. This isn't just an academic exercise for particle physicists. The mass hierarchy of neutrinos is a master key that unlocks our understanding of everything from the inner workings of atomic nuclei to the fate of the entire cosmos. These tiny weights have colossal consequences. For instance, the hierarchy determines how neutrinos behaved in the extreme conditions of the early universe, which in turn influenced how the first atoms formed and how matter clumped together to form the vast cosmic web of galaxies we see today. The gravitational pull of all those neutrinos over billions of years has subtly sculpted the universe's largest structures. Knowing their mass order would tell us exactly how that sculpting took place. Furthermore, the hierarchy is a critical clue to physics beyond our current standard model. Why are neutrinos so unimaginably lighter than every other fundamental particle? The electron, for example, is at least over 1,000,000 times heavier than even the heaviest neutrino. This is one of the greatest mysteries in physics, and the mass ordering points toward the solution. Certain theories that attempt to explain this extreme lightness predict a normal hierarchy, while others predict an inverted one. Without knowing the order, we're essentially guessing which path to take in our quest for a deeper theory of the universe. This is where the Cosmic Neutrino Background becomes our most powerful telescope. While Earth-bound experiments struggle with the faint signals of modern neutrinos, the relic background is a fossilized snapshot from a time when the universe was a searingly hot plasma. In that dense environment, the way neutrinos interacted with each other and with other particles was exquisitely sensitive to their individual masses. The specific patterns that were imprinted onto this ancient sea of particles, patterns that were then frozen in place as the universe expanded and cooled, hold a perfect record of the mass hierarchy. As these primordial neutrinos streamed across the young cosmos, their gravity subtly affected the distribution of dark matter and the primordial gas that would eventually form galaxies. The specific way they did this depended entirely on whether their masses were normally or inversely ordered. By creating incredibly detailed maps of the universe's large-scale structure, charting the distribution of millions of galaxies across billions of light-years, cosmologists can look for the faint gravitational imprint left by these ancient neutrinos. It's a cosmic detective story where the clue is the very shape of the universe itself. By comparing these ultra-precise observations with predictions from supercomputer simulations of both hierarchy scenarios, we may finally get our answer. The silent whisper of the cosmic neutrino background, echoing from the first second of time, might be the one thing clear enough to tell us the true weight of these spectral particles. Yet the mystery of their mass is just one piece of a far larger cosmic puzzle. As we peer into the depths of space, we are confronted by an even more enigmatic presence, a substance that makes up the vast majority of the universe's matter yet reveals itself only through its ghostly gravitational pull. This, of course, is dark matter, and our journey into the cosmic neutrino background now leads us to a thrilling and deeply speculative frontier, the possibility that these two great mysteries of the cosmos are intimately connected. Could these ancient relic neutrinos be interacting with dark matter, or perhaps even be a part of it? This idea transforms neutrinos from mere silent witnesses into potential portals for understanding the universe's invisible majority. To grasp why this connection is so compelling, we must first appreciate the sheer dominance of dark matter. For every ounce of the visible universe, every star, every planet, every human being, there is nearly 6 times more dark matter. It is the hidden scaffolding upon which galaxies are built. Without its immense gravitational glue, spinning galaxies would simply fly apart. But after decades of searching, we still have no idea what it actually is. We can map its distribution across the cosmos, but we cannot see it or touch it. It is the ultimate cosmic ghost, much like the neutrino, but on a vastly larger scale. This similarity is not lost on physicists. Both neutrinos and dark matter particles are elusive, neutral, and only interact significantly through gravity and possibly the weak nuclear force. This has led to a fascinating class of theories where dark matter isn't some entirely separate, exotic entity, but is instead part of a larger, hidden sector of particles that interacts with our familiar world primarily through the neutrino. In this scenario, the cosmic neutrino background could act as a cosmic messenger, a go-between that carries information from the shadowy realm of dark matter into our visible universe. One provocative idea is that dark matter particles might actually decay into neutrinos. If this were happening across the universe, it would inject a unique, high-energy signature into the ancient sea of cosmic neutrinos that we might eventually learn to recognize. Our detectors could one day pick up an anomalous number of neutrinos streaming from regions of space densely packed with dark matter, like the centers of galaxies, providing our first indirect glimpse of dark matter decay. Perhaps even more mind-bending is the theory of secret interactions. This proposes that dark matter particles don't just ignore normal matter, they might also be ignoring each other, only communicating through a mysterious fifth force of nature that we cannot perceive. But what if neutrinos are the exception? What if they can feel this force, the relic neutrinos from the Big Bang, coursing through vast halos of dark matter that surround galaxies? could have been subtly nudged and scattered by these secret interactions over billions of years. This scattering would have left a faint but specific imprint on how both the neutrinos and the dark matter are distributed in space. By meticulously mapping the large-scale structure of the universe and comparing it to the expected behavior of the cosmic neutrino background, cosmologists are essentially hunting for the gravitational fingerprints of this incredible conversation between two ghosts. The most radical proposal of all is that certain types of neutrinos could actually be the dark matter. This was an idea scientists seriously considered for a time. However, we now know that the three standard neutrinos of the Standard Model are far too light and fast-moving to account for the clumpy, gravitational scaffolding we observe. They are hot dark matter, and simulations show that a universe built on hot dark matter would look nothing like our own. Galaxies would never have formed. But the door is not completely closed. The hunt is now on for a theoretical fourth type of neutrino, often called a sterile neutrino. This particle would be even more elusive than its relatives, interacting only through gravity, making it a perfect dark matter candidate. If sterile neutrinos exist and have the right mass, they could have been produced in abundance in the Big Bang and now form the cold, slow-moving dark matter that holds the cosmos together. The subtle gravitational effects of the cosmic neutrino background could be the very thing that eventually confirms or denies their existence. This potential bridge between the universe's oldest particles and its most abundant matter is what makes this mystery so profound. We are not just looking for one answer, but for a Rosetta Stone that could decipher two of the greatest enigmas of modern science at once. The cosmic neutrino background is no longer just a fossil. It is a potential key, a cosmic translator that might finally allow us to listen in on the hidden conversations that shaped everything we see. So far, we've treated these ancient neutrinos as eternal travelers, unchanging relics from the first second that have simply flown in a straight line ever since. But this assumption of stability is just that, an assumption. And it leads us to a profound and unsettling possibility. What if these ghostly particles are not immortal? What if, over the unimaginably vast eons of cosmic time, they have slowly been fading away? This is the mystery of neutrino decay, a concept that, if proven, would force us to tear up the standard textbook on particle physics and start anew. In the world of subatomic particles, stability is the exception, not the rule. Most of the familiar particles that make up our world are inherently unstable. A neutron isolated outside an atomic nucleus will decay into a proton, an electron, and a neutrino in a matter of minutes. Even protons, the bedrock of atoms, are predicted by many grand unified theories to decay, albeit over timescales so long that the universe hasn't yet been old enough for us to witness it. Given this context, the idea that neutrinos might be fundamentally stable particles is actually a rather bold claim. The possibility that they too could transform, shedding their identity over trillions of years, is not just plausible to many physicists, it's an attractive solution to several puzzles. The most straightforward implication of neutrino decay would be a direct solution to the missing neutrinos paradox we discussed earlier. Our models predict a specific, vast density of relic neutrinos permeating all of space. But if these particles have a finite lifespan, then a significant portion of the primordial sea born in the Big Bang would have already vanished, decaying into even lighter, even more invisible particles. They aren't missing, they've simply ceased to exist in their original form. The population we're trying to detect today would be just a faint remnant of the original torrent, explaining why our counts consistently come up short. But the ramifications go far beyond just accounting for particles. The mere fact of neutrino decay would be a direct window into physics operating at energy scales we could never hope to replicate in a laboratory. For a neutrino to decay, it must transform into something else, and the rules of physics are very strict about what that something else can be. the most likely products would be a much lighter neutrino and a very low energy particle of light, a photon. This is a process that is completely forbidden in the current standard model of particle physics. Discovering it would be incontrovertible proof that our model is incomplete, that there are new forces or new particles governing neutrino behavior that we have not yet discovered. It would be the smoking gun for a revolution in our understanding of the fundamental laws of the universe. This is where the cosmic neutrino background transforms from a fossil into the most sensitive particle detector imaginable. We cannot watch a single neutrino for 14 billion years to see if it decays, but we can look for the cosmic scale consequences of that decay happening everywhere at once. One of the most promising methods is to search for a faint, universal glow of light that should have been produced if the decay into photons happened on a large enough scale. This would not be a light you could see with a telescope. It would be a specific, subtle signature embedded in the broader energy spectrum of the universe, a telltale excess of radiation that has no other obvious explanation. Astronomers are already scouring data from telescopes across the electromagnetic spectrum, from radio waves to gamma rays, searching for this ghostly echo of disappearing neutrinos. Another approach is to study the gravitational influence of the neutrino background itself. If a large fraction of the relic neutrinos have decayed away, their collective mass, and thus their gravitational pull on the large-scale structure of the universe, would be weaker than our models predict. By creating exquisitely detailed maps of how galaxies cluster together and how dark matter is distributed, cosmologists can weigh the cosmic neutrino background indirectly. If that weight is significantly less than expected, decay becomes a very compelling explanation. We are, in effect, weighing a ghost and using the result to determine if it is slowly fading from existence. The lifetime of a particle is a window into its soul, a measure of its connection to the deeper laws of reality. The quest to determine if the universe's oldest particles are eternal or ephemeral is more than just accounting. It is a direct probe into the fabric of physics itself. The silent, pervasive sea of cosmic neutrinos holds this secret, and unlocking it would not just solve a mystery, but would unveil a new chapter in the story of the cosmos. Now, let's turn our attention to a mystery that gets to the very heart of cosmology's predictive power, the temperature of this ancient neutrino sea. We've established that the cosmic neutrino background is the oldest fossil in the universe, but just how cold is this fossil today? This isn't a trivial question. In fact, it's a calculation that physicists can perform with what should be breathtaking precision. According to our standard model of cosmology, the temperature of the neutrino background is not a free parameter. It's a direct, locked-in consequence of well-understood physics from the universe's first second. And yet, this very prediction is now at the center of a growing puzzle, a subtle mismatch that could be a tiny crack in our foundational theories or a signpost to a wilder cosmic history. To understand the prediction, we need to go back to that moment of decoupling, when the weak force separated and set the neutrinos free. At that instant, the universe was a thermal bath of radiation, with everything photons, electrons, neutrinos sharing the same scorching temperature. As the universe expanded, this radiation cooled. The wavelengths of all these particles were stretched by the expansion of space itself, a process we call cosmological redshift. The critical piece of the puzzle is that we know exactly how this cooling should have proceeded for the photons, which we detect today as the cosmic microwave background at a frigid 2.725 degrees above absolute zero. The neutrinos decoupled just a moment earlier, and their cooling history is intimately tied to that of the photons. Our models predict that because of a specific event that happened to the photons after the neutrinos had left, the cosmic neutrino background should be precisely a factor of the fourth root of 4/11 colder than the photon background. That works out to a predicted temperature of about 1.945 Kelvin, just under 2 degrees above absolute zero. This number isn't a guess, it's a firm prediction derived from the bedrock physics of the Big Bang. The problem is that this prediction rests on a set of assumptions about how the universe behaved in that first second, assumptions that we are now beginning to question. The discrepancy, the temperature puzzle, arises when we try to measure this neutrino temperature indirectly. Since we can't detect these relic neutrinos directly, we have to look for their gravitational influence on other things we can see, like the distribution of galaxies in the universe or the precise properties of the cosmic microwave background. Some of these ultra-precise cosmological observations seem to suggest a neutrino background that is slightly colder than our theoretical prediction expects. The difference is minute, a fraction of a degree, but in the world of precision cosmology, even a tiny deviation can be a thunderclap. It suggests that our standard story of the universe's early cooling might be missing a chapter. So what could have made the neutrino background colder than expected? Physicists are exploring several fascinating possibilities. One leading idea involves the existence of entirely new, lightweight particles that we haven't yet discovered. Imagine if, shortly after the neutrinos decoupled, a new type of particle emerged from the vacuum and decayed, dumping its energy into the primordial plasma. This sudden injection of energy would have preferentially reheated the photon bath. The neutrinos, already decoupled and flying free, would have missed this cosmic warming event entirely. The photons get a boost, but the neutrino temperature remains unchanged, creating a wider gap between the two backgrounds than our standard models predict. The observed temperature of the neutrino sea would, in effect, be colder relative to the photons. This would be a direct signature of physics beyond the standard model, a fossilized record of a particle that vanished almost immediately after it appeared. Another possibility is even more profound. It could point to a fundamental misunderstanding of how gravity itself works on cosmic scales, or an unusual phase in the universe's expansion history. What if dark energy, the mysterious force accelerating the expansion of the universe, wasn't constant? What if it was stronger in the past? A period of faster-than-expected expansion would have stretched the neutrino wavelengths more aggressively, cooling them further than our standard calculations account for. Alternatively, theories that modify Einstein's general relativity to explain dark energy often make specific predictions about how the growth of cosmic structures is influenced by neutrinos. A measured temperature that is off by even a small amount could be the key piece of data that helps us choose between competing theories of gravity itself. This temperature puzzle is a beautiful example of how cosmology works. We take a bold, precise prediction from our best theories and then scour the universe for any tiny deviation. That deviation isn't a failure, it's a clue. The predicted temperature of 1.945 Kelvin is a bullseye on a target. The fact that our observational arrows might be landing just a hair off-center doesn't mean we're bad shots. It means there's a breeze we hadn't accounted for, a subtle, new physical effect that gently nudged the arrow in flight. By studying this coldest of fossils, we aren't just measuring a number, we are taking the temperature of the entire universe's history. And the reading is telling us that the story might be even richer and more strange than we ever imagined. This journey into the coldest reaches of cosmology leads us to a mystery of profound transformation, a dramatic shift in the very nature of the universe's first particles. We are familiar with phase transitions in our daily lives: water freezing into ice or boiling into steam. These are changes in the state of matter driven by temperature and pressure. Now consider the possibility that the entire sea of cosmic neutrinos, in the extreme conditions of the infant universe, underwent a similar, though far more exotic, metamorphosis. This is not about freezing or boiling, but about a fundamental reorganization of the neutrino's quantum properties, a shift that could have sent ripples through the fabric of spacetime itself, leaving a permanent mark on the cosmic neutrino background. To understand how this could happen, we need to envision the universe not just as an expanding fireball, but as a quantum field. In modern physics, every fundamental particle is considered an excitation, a tiny ripple in its own underlying field that permeates all of space. The electron has its field, the quark has its field, and of course the neutrino has its neutrino field. The state of this field is not always constant. It can change dramatically based on the energy of the environment. In the incredibly hot and dense early universe, the neutrino field would have been in a high-energy, symmetric state. Think of it like a perfectly balanced pencil standing on its point. It's a possible state, but it's wildly unstable. As the universe expanded and cooled past a critical threshold, this neutrino field would have undergone a spontaneous symmetry breaking, suddenly settling into a new, stable, and lower energy state. This is the phase transition. It's as if that pencil suddenly chose a direction and fell over. But for a quantum field, this falling isn't a physical movement. It's a fundamental change in the vacuum of space itself, and it would have happened everywhere in the universe at once in an instant. The consequences of such an event would have been nothing short of cosmic. When water freezes into ice, it expands and releases latent heat. A neutrino phase transition would have also released a colossal amount of energy, but in the form of gravitational waves, ripples in the fabric of spacetime. These wouldn't be the violent waves from merging black holes that our detectors like LIGO and Virgo are tuned to find. These would be primordial gravitational waves with wavelengths so long they could span the entire observable universe and frequencies so low they are virtually frozen. They would form a stochastic background hum, a gravitational analog to the cosmic microwave background. If this transition was strongly first order, meaning it occurred through the violent process of bubbles nucleating and colliding, like the rapid boiling of a superheated liquid, it would have been an event of unimaginable ferocity, generating a gravitational wave signal potentially strong enough to be detected by future observatories like the space-based LISA mission. But the most tantalizing imprint might be left on the cosmic neutrino background itself. A phase transition could have dramatically altered the neutrinos' effective mass and their interactions with each other. Before the transition, they might have been effectively massless. After, they gained their tiny but crucial mass. This sudden change would have instantly modified the gravitational influence of the entire neutrino sea. This shift would have affected how both dark matter and ordinary matter began to clump together to form the first galaxies. The specific patterns in the universe's large-scale structure, the cosmic web of clusters and filaments that we map with telescopes, could therefore contain a frozen record of this ancient neutrino metamorphosis. By comparing ultra-precise observations of the cosmos to advanced computer simulations that include such phase transitions, cosmologists are hunting for a subtle but distinct signature in the distribution of galaxies that points to this dramatic event. This idea pushes our understanding from the realm of smooth evolution into the domain of sudden, revolutionary change. It suggests that the properties of the neutrino we measure today were not forged gradually, but were locked in during a single, catastrophic instant when the universe was less than a second old. The search for evidence of this transition is a search for a moment of cosmic decision, a time when the neutrino field chose its path and in doing so, helped write the rules for the structure of everything that was to come. So far, we've considered the cosmic neutrino background as a uniform sea, a perfectly smooth relic from the dawn of time. But what if this ancient fossil isn't perfectly smooth at all? What if imprinted upon it are the faintest of patterns, tiny variations in density and temperature that tell a story of the universe's turbulent birth? This is the anisotropy mystery, and searching for these subtle wrinkles is one of the most ambitious endeavors in all of cosmology. We know such patterns exist in the cosmic microwave background, the light that was set free 380,000 years after the Big Bang. Satellite maps from Planck and WMAP reveal a beautiful speckled pattern of hot and cold spots. These anisotropies are the seeds of all structure in the universe, the gravitational blueprints for every galaxy, cluster, and supercluster we see today. They are the amplified echoes of quantum fluctuations, tiny ripples in the fabric of space-time that were stretched to cosmic proportions during a period of rapid inflation in the universe's first fraction of a second. The neutrino background, being orders of magnitude older, should contain its own version of this pattern, a primordial imprint from a time when the universe was far hotter, denser, and more chaotic. The potential information locked in these neutrino anisotropies is staggering. Because neutrinos decoupled just 1 second after the Big Bang, their patterns were frozen into place long before the patterns in the light background. This means they offer a snapshot of the universe at a much earlier, more pristine stage. Any anisotropies in the neutrino sea would be entirely unaffected by the complex physics that later shaped the photon background processes like sound waves traveling through the primordial plasma or the scattering of light off free electrons. The neutrino map would be a cleaner, more direct record of the initial conditions set by inflation. Comparing the two maps, the neutrino blueprint and the photon blueprint, would allow us to witness for the first time how the raw potential of the infant universe evolved into the complex cosmic web we observe today. But here lies the immense challenge. Detecting these patterns seems almost fantastically difficult. The anisotropies in the cosmic microwave background are on the order of 1 part in 100,000. The variations in the neutrino background are predicted to be even fainter. We are trying to discern the faintest of whispers etched onto a signal we cannot even directly hear. Our current technology is nowhere near sensitive enough to make such a measurement. It would require a neutrino detector of literally astronomical proportions, perhaps a future observatory that uses an entire planet as its sensor medium. Yet cosmologists are not without hope. While a direct detection remains a dream for the distant future, we can hunt for the gravitational ghost of these anisotropies. The subtle variations in the density of the relic neutrino sea would have created corresponding variations in their gravitational pull. This would have left a specific, faint imprint on the distribution of dark matter in the early universe, which in turn influenced how the first galaxies formed. The large-scale structure of the universe today, the immense cosmic web of filaments and voids, may therefore contain a hidden signature of those primordial neutrino patterns. By creating exquisitely detailed three-dimensional maps of billions of galaxies, projects like the Dark Energy Spectroscopic Instrument are essentially conducting an archaeological dig through cosmic time. They are searching for a specific statistical signature in the way galaxies cluster that can only be explained by the gravitational influence of an anisotropic neutrino background. Finding this signature would be a monumental discovery. It would not only confirm the existence of these patterns, but would provide a powerful new test for theories of inflation. Different models of inflation predict different statistical properties for the initial quantum seeds. Some predict Gaussian fluctuations, others non-Gaussian. Some predict a specific tilt in the spectrum of fluctuations, others do not. The neutrino anisotropies, being the oldest imprint, would be the ultimate arbiter, telling us which inflationary models best match reality. Furthermore, because neutrinos free streamed across the young universe, they would have subtly washed out some of the smallest scale anisotropies through their movement. The precise amount of this smoothing effect depends directly on the mass of the neutrinos. A detection of the anisotropy spectrum would therefore give us an incredibly precise, independent measure of the neutrino's mass, potentially solving the hierarchy conundrum from Mystery 3 in a single stroke. The search for anisotropy transforms the cosmic neutrino background from a passive fossil into an active historical document. Its uniformity is a profound assumption, but its non-uniformity, should we ever detect it, would be a revelation. It is the ultimate treasure map, its faint contours charting a course not just through space, but back to the very first instant of time, waiting for a generation of scientists advanced enough to finally read it. The story of the cosmic neutrino background is one of ghostly isolation, of particles so aloof they barely acknowledge the existence of other matter. But this narrative of the lone wolf neutrino might be incomplete. What if, in the searing density of the first second, these particles were not solitary ghosts but social butterflies, interacting with each other in ways we have never witnessed? This is the intriguing mystery of neutrino self-interactions, a possibility that introduces the potential for complex collective behaviors within this ancient sea, behaviors that could have dramatically reshaped the early cosmos. Our standard model of particle physics is very clear on this point. Neutrinos should not interact with each other. They have no electric charge, so they cannot exchange photons the way electrons do. And while they do feel the weak nuclear force, its incredibly short range means the chance of two neutrinos passing close enough to interact is vanishingly small. In the vast emptiness of today's universe, this is almost certainly true. But the universe 1 second after the Big Bang was a different place entirely. It was over 1 billion times denser than it is today, crammed with a ferocious density of particles. In that primordial crowded room, even the most antisocial particles might have been forced to mingle. This has led physicists to speculate about the existence of a secret neutrino interaction. This is the idea that there might be a new, as yet undiscovered fifth force of nature that operates exclusively within the neutrino family. This force would be carried by a hypothetical new particle, perhaps a very lightweight boson sometimes called a majoron. If such a force exists, it would have been a powerful influence only when neutrinos were packed together cheek by jowl in the early universe. These self-interactions could have caused the sea of cosmic neutrinos to behave less like a collection of independent particles and more like a fluid, with its own internal pressure, viscosity, and even the potential to form collective waves or oscillations that rippled through the young cosmos. The consequences of such a phenomenon are profound. Imagine a dense crowd of people all trying to move through a narrow space. If everyone ignores each other, they might eventually get through, but it will be a chaotic and inefficient process. Now imagine if everyone in that crowd could subtly communicate and coordinate their movements. The flow would become smoother, more organized. This is what neutrino self-interactions could have done. In the early universe, this coordinated flow would have affected how the neutrino sea gravitationally influenced the clumping of dark matter. The specific pattern of how galaxies and clusters are distributed across the universe today might therefore contain a hidden signature of this ancient coordinated neutrino behavior. We are only now, with powerful new telescopes, beginning to see hints in the large-scale structure that could be explained by this very effect. Furthermore, these self-interactions could act as a powerful eraser, smoothing out the primordial anisotropies we just discussed. Free-streaming neutrinos moving independently would only dampen the smallest scale fluctuations, but a neutrino fluid interacting strongly with itself would have a much larger collective effect, washing out a greater portion of the early density variations. The statistical signature of this enhanced smoothing would be distinctly different, offering cosmologists another clue to look for in their maps of the cosmic web. It would also mean that our current estimates of the neutrino's mass, which are based on the assumption of free streaming, might need a significant revision if this fluid-like behavior was occurring. The most dramatic possibility involves the potential for these interactions to trigger a cosmic phase transition within the neutrino sea itself, a sudden shift from a state of free particles to a correlated superfluid. Such a transition would not be gentle. It could have generated a background of primordial gravitational waves with a unique frequency signature, a ringing in spacetime that future observatories might one day detect. It also opens a door to understanding one of the universe's great asymmetries, why we live in a world made of matter with almost no antimatter to be found. Certain types of neutrino self-interactions are capable of violating a fundamental symmetry of nature called CP symmetry, which governs the difference between matter and antimatter. If these interactions were strong enough in the early universe, they could have been the engine that preferentially produced more matter neutrinos than antimatter neutrinos, setting the stage for the matter-dominated cosmos we inhabit today. The ghostly sea of relics around us could be the faded evidence of the process that made our very existence possible. This profound question of why we exist at all leads us to one of the most beautiful and fundamental mysteries in all of science, the matter-antimatter asymmetry of the universe. Why is there something rather than nothing? According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. When these two opposing kinds of particles meet, they annihilate each other in a flash of pure energy. If the initial creation had been perfectly balanced, every particle of matter would have found its antimatter twin, and the entire universe would have annihilated into a featureless sea of radiation, leaving no atoms, no stars, no planets, and certainly no us. The fact that we are here in a universe filled with galaxies is absolute proof that this symmetry was broken. Somehow, for every billion pairs of matter and antimatter particles that annihilated in the early fireball, one single matter particle was left over. That 1 in a billion surplus is everything we see today. The search for the mechanism behind this miracle, known as baryogenesis, is a holy grail of physics, and the cosmic neutrino background might be hiding the answer. The puzzle is that the standard model of particle physics, for all its successes, cannot account for this asymmetry. It simply doesn't produce a large enough imbalance. To create such a profound violation of the initial symmetry, any viable theory must satisfy three conditions known as the Sakharov criteria. First, there must be a process that violates the conservation of baryon number, meaning it can create more matter than antimatter. Second, the laws of physics must treat matter and antimatter slightly differently, a violation of something called C and CP symmetry. And third, this all must have occurred out of thermal equilibrium, meaning it happened during a rapid, disruptive phase of the universe's expansion before things could even out. The cosmic neutrino background is a pristine relic from the exact era when these conditions could have been met, making it a potential witness to the very event that made our existence possible. This is where neutrinos themselves become the prime suspects. Their mysterious properties make them ideal candidates for the engine of baryogenesis. We know that neutrinos violate a fundamental symmetry. They oscillate between different types, and it turns out that antineutrinos oscillate at a slightly different rate. This is a direct violation of CP symmetry, checking one of Sakharov's crucial boxes, but the effect in the standard model is far too small to account for the universe we see. However, if we look beyond the standard model to more exotic theories, the potential grows dramatically. Many of these theories involve very heavy, right-handed neutrinos that could have existed only in the extreme energy of the very early universe. These particles would have been tremendously unstable, decaying out of thermal equilibrium. Crucially, due to their inherent CP-violating properties, these decays might not have been equal. They could have produced just a tiny fraction more matter particles than antimatter particles in their decay products. This is where the cosmic neutrino background enters the story as a silent ledger. The same CP-violating processes that generated the matter asymmetry would have also imprinted a specific, subtle polarization onto the sea of relic neutrinos that were present at the time. It would have created a slight preference and handedness in the way those ancient neutrinos spin as they travel through the universe. This polarization is a fossil that should still be present today, frozen into the cosmic neutrino background. If we could ever find a way to detect it, measuring this faint spin preference would be like reading the original cosmic accounting book, directly confirming that neutrinos were the architects of our material world. Furthermore, the gravitational influence of this asymmetric neutrino sea would have left a mark on the formation of the universe's largest structures. The specific way that the leftover matter began to clump under gravity would have been ever so slightly different if the initial asymmetry was generated by neutrinos versus some other, more exotic particle. The next generation of cosmological surveys, which will map billions of galaxies with incredible precision, will be sensitive enough to look for this specific statistical fingerprint in the cosmic web. While we may not be able to detect the relic neutrinos directly for a very long time, we might soon have indirect but compelling evidence that they are the reason anything exists at all. The ghostly sea from the first second may not just be a relic of creation, but the very reason creation had a material outcome. This brings us to an enigma that challenges our very understanding of what a neutrino is capable of. We've grown accustomed to thinking of them as utterly neutral, ghostly passengers in the cosmos, indifferent to the electromagnetic forces that govern light and matter. But what if that's not the entire story? What if these neutral particles harbor a hidden sensitivity, a ghost of a magnetic personality? This is the compelling mystery of the neutrino magnetic moment, a tiny, theoretical property that could allow these spectral particles to feel the universe's magnetic fields and, in doing so, leave a unique signature on the cosmic neutrino background for us to find. To grasp this idea, we need to step back and consider what a magnetic moment represents. For a particle like an electron, it's straightforward. It's like a tiny bar magnet with a north and south pole, generated by its electric charge and its spin. This is why electrons respond to magnetic fields, but a neutrino has no electric charge. How could something fundamentally neutral have any magnetic character at all? The answer lies in the bizarre world of quantum mechanics. According to theory, even a neutral particle can develop a tiny magnetic moment through quantum loop processes virtual particles flickering in and out of existence around the neutrino, granting it a fleeting, infinitesimal electromagnetic shadow. In the standard model of particle physics, this effect is predicted to be so incredibly small as to be virtually undetectable. But many theories that extend beyond the standard model predict that the neutrino's magnetic moment could be significantly larger, perhaps by many orders of magnitude. Finding evidence for this would be a direct portal into new physics. Now, consider the stage. The cosmic neutrino background is a sea of these particles that has been streaming across the universe for nearly 14 billion years. During that immense journey, they have passed through galaxies, clusters, and the vast voids between them, regions that are permeated by magnetic fields. These cosmic magnetic fields are weak by earthly standards, but they are immense in scale, stretching for millions of light years. If relic neutrinos possess even a minuscule magnetic moment, these sprawling magnetic fields would have acted upon them. The magnetic field would have gently torqued the spin of the neutrinos, causing them to gradually precess, much like a spinning top slowly wobbles under Earth's gravity. Over billions of years, this subtle interaction could have collectively aligned the spins of the neutrinos in a specific direction, imparting a large-scale polarization to the entire cosmic neutrino background. This sea of ancient particles wouldn't be random. It would have a preferred orientation, a faint cosmic magnetism etched into its very fabric. The potential for detection, while enormously challenging, is breathtaking. We could not see this polarization directly, but its gravitational influence would be profound. A polarized neutrino background would exert a directional gravitational pull on the matter in the universe. This would not be a force that pulls equally in all directions. It would have a slight preference, an anisotropy that could subtly influence how galaxies and clusters align with each other over vast distances. This is a phenomenon known as intrinsic galaxy alignment, and while it can have other causes, a specific, universal pattern of alignment that correlates with the known direction of cosmic magnetic fields could be the telltale fingerprint of a magnetically active neutrino sea. Next-generation sky surveys, like those from the Vera C. Rubin Observatory, will map the shapes and orientations of billions of galaxies with unprecedented precision. Within that immense dataset, cosmologists will be searching for this very signal, a faint but coherent pattern in how galaxies point, a whisper of magnetism from the first second of time. Beyond just a curious property, a detectable magnetic moment would fundamentally reshape the story of the early universe. In the first seconds after the Big Bang, the cosmos was a dense plasma, and powerful magnetic fields may have already been present. If neutrinos had a significant magnetic moment, they could have played a role in amplifying those nascent fields or transferring energy through the plasma in unique ways. Furthermore, this magnetic interaction offers a potential new solution to the missing neutrinos paradox. If relic neutrinos can feel magnetic fields, they might be more likely to interact with other particles in ways we haven't considered, or even be scattered or focused by magnetic fields in galactic halos, altering their distribution and making them appear missing from our simple counts. The search for this hidden magnetism transforms the cosmic neutrino background from a passive fossil into an active participant in cosmic evolution, a sea of particles that may have been subtly guided by the magnetic heartbeat of the universe itself. But to truly appreciate the power of this fossil, we must journey even further back in time, to an era so early that it defies our everyday intuition. We're talking about a fraction of a second so small it's almost meaningless to write down, a period known as the inflationary epoch. This was the universe's dramatic opening act, a burst of exponential expansion that smoothed out the cosmos and planted the seeds for everything to come. Incredibly, the ghostly sea of neutrinos might hold the clearest record of this primordial event, offering a window into that first moment that even light itself cannot provide. Inflation is a cornerstone of modern cosmology, but it remains a theory. We see its proposed effects everywhere in the overall flatness of the universe, its large-scale uniformity, and the specific pattern of speckles in the cosmic microwave background. But we have no direct proof of the inflationary field, the mysterious energy that supposedly drove this fantastical expansion. Different models of inflation make different predictions, and we are left trying to piece together what happened by studying its aftermath, like detectives arriving at the scene long after the event. The cosmic microwave background has been our primary witness, but it only testifies to the state of the universe 380,000 years after the Big Bang. The neutrino background, by contrast, carries information from the first second, placing it immeasurably closer to the inflationary event itself. It is a witness that was present in the courtroom from the very first gavel strike. The critical link lies in those primordial anisotropies, the tiny density variations we discussed earlier. According to inflationary theory, these variations were born from quantum fluctuations in the inflationary field itself. Microscopic ripples in the fabric of spacetime were stretched to astronomical sizes during the rapid expansion, becoming the gravitational seeds for all future structure. The cosmic microwave background shows us these seeds after they have been processed and altered by 380,000 years of complex physics in the primordial plasma. Sound waves traveled through this hot soup, scattering photons and blurring the original imprint. The neutrino background, however, decoupled before most of this processing could occur. Its pattern of anisotropies is a much cleaner, more direct fingerprint of those initial quantum seeds. It is the original high-resolution photograph compared to the somewhat blurred and edited version we get from the light background. This purity makes the cosmic neutrino background the ultimate test for inflationary models. Different theories of inflation predict different statistical properties for these initial fluctuations. Some predict they follow a perfectly Gaussian or random distribution. Others predict subtle deviations from Gaussianity, specific twists in the pattern that would be a smoking gun for a particular type of inflationary physics. The patterns imprinted on the neutrinos would preserve these statistical details with far greater fidelity. Furthermore, the gravitational influence of these pristine neutrino fluctuations would have been the very first to begin tugging on dark matter, starting the process of gravitational collapse that eventually formed galaxies. The large-scale structure of the universe today may therefore contain a hidden, amplified record of the neutrino anisotropy spectrum. By mapping the cosmos in incredible detail, we are essentially performing a form of cosmic archaeology, digging down through layers of time to uncover the original blueprint laid down by inflation. The potential doesn't stop there. Certain ambitious models of inflation propose that the violent process of exponential expansion did more than just stretch quantum fluctuations. It may have created a background sea of primordial gravitational waves. These ripples in spacetime would have interacted with every particle in the early universe, including neutrinos. This interaction could have polarized the cosmic neutrino background in a specific, unique way, imparting a telltale swirl to its distribution. Detecting this polarization, even indirectly through its effect on galaxy formations, would be direct, uncontestable evidence for inflation and would immediately tell us the energy scale at which it occurred, a fundamental parameter we currently have no way of measuring. While we may never be able to directly detect the cosmic neutrino background, its ghostly gravitational hand has been shaping the universe for billions of years. By reading the story written in the positions and motions of galaxies, we might finally be able to read the first page of that story, written by inflation and delivered to us by the most ancient and faithful messengers in the cosmos. Now we venture into one of the most speculative and thrilling mysteries of all, the hunt for a ghost within a ghost. For all their strangeness, the three known types of neutrinos still operate within the rules of our standard model of physics. But what if there's a fourth, a neutrino so secretive, so utterly aloof, that it doesn't even interact via the weak nuclear force, the one tenuous connection its relatives have to the rest of the universe? This is the concept of the sterile neutrino, a hypothetical particle that could be the key to unlocking not only the secrets of the cosmic neutrino background, but also the true nature of dark matter itself. The motivation for such an outlandish idea comes from a series of stubborn experimental anomalies that have plagued physicists for decades. In several different labs around the world, from nuclear reactors to particle accelerators, researchers have detected curious discrepancies in the number of neutrinos they observe and the ways they seem to oscillate or change flavor. The data seems to suggest that neutrinos might be transforming into a fourth type that our detectors cannot see, a particle that is completely invisible to our instruments because it simply ignores the weak force. This elusive entity is what we call a sterile neutrino. It's sterile because it is inert, completely clean of any interaction with the known forces except for gravity. If it exists, it would be a direct portal into a hidden sector of particles, a whole shadow universe of matter that operates by its own rules, parallel to our own but forever just out of reach. This is where the ancient sea of cosmic neutrinos becomes our most powerful investigative tool. The presence of sterile neutrinos in the early universe would have dramatically altered the thermal history of creation. If sterile neutrinos were popping in and out of existence in the first second, they would have acted as an extra energy sink, cooling the primordial plasma faster than our standard models predict. This would have left a distinct, fossilized imprint on the relative temperatures of the cosmic neutrino background and the cosmic microwave background. The subtle cooling discrepancy we might be seeing today could be the direct signature of this extra, hidden particle diluting the energy of the young cosmos. Furthermore, the gravitational influence of a sea of sterile neutrinos would be immense. They would have affected the rate at which the first structures in the universe condensed out of the primordial soup. Different masses for the sterile neutrino would produce different patterns in the cosmic web of galaxies we see today. A light sterile neutrino would behave as hot, dark matter, smoothing out small-scale structures, while a heavier one could be a perfect candidate for warm, dark matter, potentially solving some long-standing puzzles about the number and distribution of small satellite galaxies around our Milky Way. By scanning the sky and mapping the universe's large-scale structure with incredible precision, Cosmologists are effectively weighing and counting these invisible particles through their gravitational footprint, hunting for the telltale signs of a hidden participant in the drama of cosmic evolution. The most profound possibility is that sterile neutrinos are not just a curiosity, they are the dark matter. A sterile neutrino with a mass of a few kilo-electronvolts could have been produced in just the right abundance in the Big Bang to account for the universe's missing mass. It would be cold, stable, and would only interact through gravity, matching the observed profile of dark matter perfectly. The relic neutrinos we've been discussing would then be joined by a vastly more abundant sea of their sterile cousins, a deep, dark ocean hidden beneath the visible universe, its gravitational waves dictating the formation of every galaxy. The cosmic neutrino background is the only place where the gravitational effects of these two seas, the active and the sterile, might be untangled, offering us our first real glimpse into the hidden sector and potentially solving the greatest mystery in modern cosmology. We are surrounded by ghosts, and some of them may be hiding in plain sight, their presence felt only by the gentle tug of gravity on the cosmos they built. This brings us to a mystery born from the very geometry of spacetime, a flaw in the fabric of the cosmos that could have left a dramatic scar on the neutrino sea. To understand it, we must consider the universe not just as an expanding fireball, but as a medium undergoing a series of rapid phase transitions. As it cooled, the fundamental fields that permeate all of reality settled into their stable states. But like water freezing into ice, this process may not have happened perfectly smoothly everywhere. In some regions, the fields might have gotten stuck, unable to settle into the lowest energy state. This could have created unimaginably narrow, incredibly dense cracks in the structure of the universe, defects of pure energy known as cosmic strings. These aren't strings in the everyday sense, they are theoretical one-dimensional scars, thinner than a proton but with the mass of a mountain range packed into every inch, stretching across the entire observable universe. For decades, they have remained a beautiful but unproven prediction of many grand unified theories. The incredible thing is that the cosmic neutrino background might be the very thing that finally reveals them. The interaction between these cosmic scars and the sea of relic neutrinos would have been a dramatic event. Picture a cosmic string, a flaw in spacetime with immense gravitational power moving through the early universe. As it slices through the dense sea of neutrinos, its tremendous gravity would act like a plow, pulling streams of these ghostly particles along with it. The string's movement would create vast, thin wakes of overdensity in the neutrino background regions where the neutrinos are bunched together, trailing behind the string like the wake behind a boat. These wouldn't be minor ripples. The gravitational tug of a cosmic string is so powerful that these wakes could become some of the most prominent features in the entire neutrino sea, creating immense linear patterns of density etched onto this ancient fossil. Furthermore, the strings themselves would have been dynamic and violent. They could have formed loops that oscillated rapidly and eventually decayed in a spectacular burst of gravitational waves. These violent events happening in a universe filled with the neutrino background would have sent powerful shockwaves through this sea. The sudden, catastrophic collapse of a cosmic string loop would have generated a spherical shell of gravitational energy that propagated outward, compressing the neutrinos in its path and leaving a distinct circular imprint in their distribution. The neutrino background would thus bear the scars of these ancient cosmic cataclysms, a permanent record of the death throes of some of the most exotic structures thought to have ever existed. The challenge, of course, is that we cannot see this neutrino tapestry directly, but we don't have to. The gravitational influence of these wakes and imprints would have been profound. The regions where neutrinos were bunched together by cosmic strings would have exerted a stronger gravitational pull on the surrounding dark matter and primordial gas. This would have seeded the formation of the very first structures in the universe in a unique way. Instead of the random, speckled pattern of anisotropies from inflation, cosmic strings would have preferentially created thin, linear filaments of matter and vast sheet-like structures. The large-scale cosmic web we see today might therefore contain the ghostly fingerprints of these strings. Astronomers are already scanning the sky, looking for perfectly straight alignments of galaxies or strangely uniform, giant voids that could only have been carved out by the passage of a cosmic string long ago. The promise of this search is immense. Finding evidence for cosmic strings would be a direct confirmation of physics at energy scales 1 trillion times beyond what our most powerful particle colliders can reach. It would tell us that the fundamental forces of nature truly were unified at the birth of the cosmos and would point us toward the correct grand unified theory. The cosmic neutrino background serves as the perfect photographic plate for recording these events because it was present at the time. It is affected only by gravity, and its patterns were frozen in place immediately. While the photon background was blurred by later interactions, the neutrino record remains sharp. The gravitational echoes of those string-induced wakes, imprinted on the distribution of galaxies across the universe, may be our best hope for discovering these cosmic scars and, in doing so, reading the deepest secrets of unification written in the first second of time. But this ancient fossil we've been exploring, the cosmic neutrino background, presents us with a profound assumption that it is a static, unchanging relic. We treat it as a snapshot, a moment frozen in time from the first second, its properties constant and eternal as it expands along with the universe. But what if this assumption is wrong? What if this ghostly sea is not a still photograph, but more like a slow-motion film? This is the time variation puzzle, a mystery that asks whether the fundamental nature of these ancient particles themselves might have evolved over the billions of years of cosmic history, and what that incredible possibility could reveal about the very laws of physics. Our standard cosmological model is built on the idea that the laws of nature are immutable. The speed of light, the strength of gravity, the mass of an electron, these are considered fundamental constants, unchanging from one end of the universe to the other and across all of time. We apply this same principle to the cosmic neutrino background. We calculate its temperature and density today based on the well-understood physics of cosmological redshift, confident that its properties have simply diluted and cooled in a predictable, linear way with the expansion of the universe. This constancy is the bedrock upon which we use it as a standard ruler to measure everything else. But what if the bedrock itself is shifting? The audacious idea here is that the properties of the neutrinos themselves, not just their distribution, could have changed over time. Could their mass have been different in the past? Could their intrinsic ability to oscillate between flavors have evolved? Or perhaps the strength of their weak interaction has subtly varied over the eons? These are not small questions. If any of these possibilities were true, it would mean that the constants of nature are not so constant after all, forcing a radical revision of our most fundamental theories. One compelling avenue for such variation involves the expansion of the universe itself and its mysterious driver, dark energy. We know the universe's expansion is accelerating, but we don't know if the strength of dark energy has been constant. If dark energy has varied over time, it would mean the rate of the universe's expansion has not been a smooth, predictable curve. Periods of faster or slower expansion would have directly affected how much the wavelengths of the relic neutrinos were stretched, effectively altering their cooling history in a way that deviates from our standard predictions. The observed temperature of the neutrino background today would then be a record not just of its initial conditions, but of the entire dynamic history of dark energy. Another, even more mind-bending possibility is that the variation is tied to the neutrino's environment. In the very early universe, the neutrino sea was incredibly dense. As the universe expanded, the density dropped dramatically. In some theoretical models, the effective mass of a particle can depend on the density of the medium it's in. It's a far-out idea, but it raises the question, Could a neutrino have had a slightly different mass when it was surrounded by trillions of its kin in the first second, compared to its mass today, flying almost alone through the vast emptiness of space? This would mean the fossil we're trying to study today is not exactly the same as the particle that was set free. It has matured and its fundamental properties have aged. How on earth could we possibly detect such a subtle, gradual change? The answer, once again, lies in the gravitational ledger of the cosmos. If the mass or other properties of the cosmic neutrinos have changed over time, it would have altered their collective gravitational influence on the formation of large-scale structures in a unique way. The specific pattern of how galaxies cluster at different distances, which correspond to different look-back times in the universe's history, might show a telltale signature. By comparing the structure of the nearby universe to the structure of the very distant universe, cosmologists can effectively look for evidence that the gravitational pull of the neutrino background was stronger or weaker in the past. It's an incredibly difficult measurement, but next-generation telescopes like the Vera-C, Rubin Observatory are designed to make exactly these kinds of ultra-precise, time-dependent maps of the cosmos. Furthermore, a time-varying neutrino background would leave an imprint on the cosmic microwave background. The gravitational potential of the neutrino sea affects how the light from the SIMB is redshifted as it travels to us, a phenomenon known as the integrated Sachs-Wolf effect. If that gravitational potential was changing over time because the neutrinos themselves were changing, it would create a specific, anomalous pattern in the SIMB that scientists could hunt for. We are already mining the Planck satellite data for any such hints, any statistical irregularities that point to a universe where the oldest particles are not quite what we thought they were. The implications of solving this puzzle are staggering. Finding evidence for time variation would be more than just a new discovery about neutrinos. It would be a revolution in physics. It would suggest that the fundamental constants might be more like dials that can be turned by the conditions of the universe, shaking the foundations of quantum field theory and our understanding of the vacuum of space itself. The cosmic neutrino background, therefore, is not just a fossil to be examined. It is a cosmic clock, one that has been ticking for 14 billion years. By learning to read its subtle tick-tocks, we might discover that time itself has changed the nature of reality, and that the universe's first particles have been evolving right alongside it, keeping a secret history of cosmic change written in their ghostly, silent journey. Now we arrive at a mystery that pushes at the very boundaries of reality itself, a frontier where our established laws of physics begin to break down and fray. For all our knowledge, we still lack a theory that successfully marries the colossal scale of gravity with the frenetic quantum world of the very small. This grand unification, a theory of quantum gravity, remains the single greatest unsolved problem in fundamental physics. The energies required to probe this realm are so astronomically high that they existed only in the first fleeting instance of the Big Bang, far beyond the reach of any conceivable particle collider. It seems we are forever locked out from directly observing this epoch. Yet there is a tantalizing possibility that a faint echo of this primeval physics was imprinted onto a messenger that has been traveling to us ever since. The cosmic neutrino background might just be our only viable telescope into the Planck scale. The core of the problem is one of energy. To see quantum gravitational effects, to witness the foam-like texture of spacetime itself, we need to probe distances on the scale of the Planck length, a size so minuscule that it is to a proton what a proton is to the entire solar system. This requires energies a quadrillion times greater than what the Large Hadron Collider can produce. It's an energy regime that has not existed since the universe was a mere 10 to the power of negative 43 seconds old, a time known as the Planck epoch. For all practical purposes, this era is completely inaccessible to direct observation. The photons of the cosmic microwave background were born hundreds of thousands of years later, far too late to carry any information from this violent quantum geometric storm. But the neutrinos are different. They decouple just 1 second after the Big Bang. While this is still an eternity after the Planck epoch, it is immeasurably closer. More importantly, their journey began in a universe that was still unimaginably dense and energetic, a place where the faintest tremors from that first moment might still have been rippling through the cosmic medium. So how could these tremors have been recorded? One compelling idea involves the concept of spacetime foam, a wild prediction of some quantum gravity theories. At the tiniest possible scales, the vacuum of space is not smooth and serene. Instead, it is thought to be a chaotic, bubbling sea where quantum fluctuations cause the very fabric of spacetime to writhe and froth. Microscopic black holes and wormholes might blink in and out of existence. In the first second, the universe was so dense that this quantum foaminess could have been a dominant feature. As the primordial neutrinos began their free-streaming journey through this seething, foamy spacetime, their paths would have been ever so slightly altered. The chaotic geometry would have acted like a complex lens, subtly deflecting the neutrinos and imparting a unique, non-random pattern to their directions. This would have created a specific kind of anisotropy in the cosmic neutrino background, not the density variations from inflation, but a distinct distortion in the velocities and paths of these ancient particles. Another potential mechanism involves the violation of fundamental symmetries. Many theories of quantum gravity predict that the supreme energy of the Planck epoch could have temporarily broken cherished symmetries of nature, such as Lorentz invariance, the principle that the laws of physics are the same for all observers, regardless of their speed or direction. If Lorentz invariance was violated, even for a fleeting moment, it could have created a preferred direction in the universe at the largest scales. This cosmic preferred frame would have left an indelible mark on the first particles to travel through it. The relic neutrinos, being the earliest free-streaming particles, would have their spins and motions aligned with this primordial directional bias. The entire cosmic neutrino background could be polarized on a universal scale, its particles subtly preferring to spin in one direction over another, a permanent fossil of a time when the rules of the game were being written. Detecting such an imprint directly is, of course, with our current technology, a fantasy. We cannot measure the path or spin of a single relic neutrino, let alone map a pattern across the entire sky. But we don't need to see the individual brushstrokes to perceive the painting. The gravitational influence of this subtly altered neutrino sea would be profound. If the neutrinos were deflected by quantum foam, their distribution would not be perfectly smooth. It would have a specific statistical roughness that would have influenced how dark matter first began to clump. This would leave a unique signature in the way galaxies are distributed in the universe today, a signature that advanced computer simulations could try to model, and that next-generation sky surveys like the Square Kilometre Array could hope to detect. Similarly, a Lorentz violating polarization would create a gravitational anisotropy, a directional tug that would subtly influence the alignment of the largest structures in the cosmos. By meticulously studying the orientations of galaxy clusters and superclusters across billions of light years, cosmologists are essentially conducting a search for this ghostly handshake from the dawn of time. The pursuit of this mystery transforms the cosmic neutrino background from a fossil into a time capsule from a realm we can never otherwise visit. It offers a potential pathway to test theories like string theory or loop quantum gravity, not in a lab, but through the cosmological consequences they predict. Each model of quantum gravity makes specific forecasts about the nature of spacetime foam and the potential for symmetry violation. The unique pattern etched onto the neutrino sea would be different for each theory. Therefore, by reading the gravitational consequences written into the large-scale structure of the universe, we might not just confirm that quantum gravitational effects occurred, we might actually be able to distinguish which theory correctly describes the universe's fundamental geometry. The silent, ancient sea of neutrinos around us may be the only witness to the universe's deepest secrets, holding within its ghostly flow the answer to the ultimate question of how spacetime itself was woven into existence. But to truly stretch our minds, we must now venture into a realm that sounds like it belongs in science fiction: the possibility that the universe contains more dimensions than the three of space and one of time we experience every day. This is not just wild speculation. It's a serious proposal from advanced physics theories like string theory, which attempts to unite gravity with the quantum world. And it leads us to a breathtaking mystery. What if neutrinos, the universe's ultimate ghosts, are not confined to our familiar four-dimensional spacetime? What if they can briefly venture into these hypothesized extra dimensions? And how would that incredible journey have shaped the cosmic neutrino background we inherit today? The concept of extra dimensions is a challenging one to visualize. We are so accustomed to living in a world of length, width, and height that imagining another spatial direction seems impossible. A common analogy is to think of our four-dimensional universe as a vast, impossibly thin membrane or brain, floating within a higher dimensional space often called the bulk. According to some models, all the particles and forces we know, quarks, electrons, photons, even ourselves, are stuck to this brain like characters drawn on a page who cannot leave the paper. But gravity and perhaps a few other special particles might be able to leak off the page and propagate into the extra dimensions. Neutrinos, with their ethereal, barely their nature, are a prime candidate for being one of these special travelers. If this is true, the implications for the early universe and its neutrino sea are profound. In the first second, the density of neutrinos was astronomical. If even a fraction of them were able to briefly tunnel into an extra dimension, it would have provided a new, unseen channel for them to lose energy or even interact with each other in ways completely forbidden in our three-dimensional space. This could have acted as a cosmic cooling mechanism, siphoning energy out of our brain and into the bulk. The result, the cosmic neutrino background in our universe, could be significantly colder than our standard models predict. The temperature discrepancy we might be observing could be the first indirect evidence that our universe is just a slice of a much larger, higher dimensional reality. Furthermore, the propagation through extra dimensions could solve several puzzles at once. The missing neutrinos paradox, where we can't account for all the relic neutrinos we expect, finds a neat explanation if a portion of them simply wandered off into another dimension and never returned. Their mass, too, could be explained by this extra-dimensional travel. In some models, a particle's mass in our universe is determined by how tightly it is bound to our brain. A particle that can easily venture into the bulk would appear very light to us. This offers an elegant explanation for why neutrinos are millions of times lighter than any other massive particle. They are simply the ones with the greatest freedom to explore the full architecture of the cosmos. Detecting this effect would, of course, be a monumental challenge, but future observatories offer a path. The gravitational influence of a neutrino sea that has been cooled or diluted by extra dimensions would be unique. It would leave a specific statistical fingerprint on the large-scale structure of the universe, a subtle deviation in the way galaxies cluster on the very largest scales that next-generation telescopes like the European Space Agency's Euclid mission are designed to map with exquisite precision. Even more tantalizing is the potential for gravitational wave astronomy. The violent process of neutrinos popping in and out of extra dimensions in the early universe could have generated a unique background hum of high-frequency gravitational waves. While our current detectors like LIGO are not sensitive to these frequencies, future space-based interferometers might one day tune into this whisper from the bulk, a direct signal that our universe has hidden depths we are only beginning to imagine. This brings us to a mystery that lies at the very frontier of cosmology, a puzzle that connects the universe's smallest particles to its largest scale behavior. We've witnessed the profound influence of dark matter, the invisible scaffolding of the cosmos, but there is another, even more enigmatic component shaping our universe's destiny: dark energy. This mysterious force is causing the expansion of the universe to accelerate, a discovery that earned the Nobel Prize and overturned our cosmic expectations. The nature of dark energy remains one of the greatest unsought problems in all of science. And now, a radical question is being asked. Could the universe's oldest particles, the cosmic neutrino background, be somehow talking to dark energy, or even be a part of its mysterious mechanism? To appreciate this connection, we need to first sit with the sheer weirdness of dark energy. Unlike any force we know, its effect is not to pull things together like gravity, or to push charges apart like electromagnetism. Instead, it behaves like a negative pressure inherent to the vacuum of space itself, causing space-time to stretch at an ever-increasing rate. The leading theoretical candidate for dark energy is the cosmological constant, an energy density that remains unchanged as the universe expands. But this simple idea comes with a colossal problem. When physicists try to calculate the predicted value of this energy from quantum theory, they arrive at a number that is 120 orders of magnitude too large. This is the worst prediction in the history of science, a clear sign that we are missing something fundamental. This vast disconnect is precisely why scientists are desperate for new ideas, and the cosmic neutrino background offers a tantalizing alternative pathway. One captivating line of thought suggests that dark energy might not be a static constant at all, but a dynamic field that has evolved over time, much like the inflationary field that powered the universe's birth. This is known as quintessence, and here is where the neutrinos come in. If this quintessence field exists, it could potentially interact with neutrinos. In the searing heat of the early universe, this interaction might have been strong, tying the behavior of the neutrino field to the behavior of the dark energy field. As the universe expanded and the neutrino sea cooled and diluted, this coupling could have triggered a phase transition in the quintessence field, causing its energy density to drop to the incredibly small, non-zero value we observe today. In this scenario, the cosmic neutrino background isn't just a passive relic. It's the catalyst that helped set the dial for dark energy, freezing it into its current state and determining the ultimate fate of the cosmos. The specific properties of the neutrinos, their mass and density, would then be directly linked to the strength of the acceleration we observe, offering a potential explanation for why dark energy has the specific value it does. Perhaps even more radical is the idea that the neutrinos themselves are the source. This might seem impossible given their tiny individual mass, but remember their staggering abundance. There are nearly 1 billion neutrinos for every proton in the universe. Their collective gravitational influence is significant. Some theories propose that as the universe expands and the relic neutrinos become more diffuse, their equation of state, the relationship between their pressure and density, could change in an exotic way. In the dense early universe, they might have behaved like normal matter, contributing to gravitational attraction. But as they became more spread out, their very quantum nature might cause them to exert a negative pressure, effectively becoming a form of dark energy themselves. This would mean the accelerating expansion isn't driven by some mysterious new field, but is a late-time consequence of the ghostly sea of particles born in the first second, a final act in their 14 billion-year journey. Testing these extraordinary ideas is incredibly difficult but not impossible. If dark energy is dynamic and coupled to neutrinos, it would leave a specific imprint on the large-scale structure of the universe. The rate at which galaxies cluster together would evolve over cosmic time in a unique way that differs from the predictions of a simple cosmological constant. The next generation of cosmological surveys, like those from the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, are designed to measure this growth of structure with unprecedented precision, hunting for any deviation that could signal this neutrino-dark energy dialogue. Furthermore, such a coupling would also affect the cosmic microwave background. It would alter the specific pattern of the temperature and polarization fluctuations we see in the SIMB in a subtle but recognizable way. Scientists are already scouring the data from the Planck satellite for any such anomalous signatures, any hint that the oldest light in the universe was shaped by an interaction between its oldest particles and its most mysterious energy. The pursuit of this mystery is a beautiful example of how science operates at its most creative edge. We are connecting the microcosm with the macrocosm, suggesting that the fate of the entire universe, whether it continues expanding forever or eventually contracts, might be written in the properties of the lightest, most elusive particles in existence. The cosmic neutrino background is no longer just a fossil to be studied. In this light, it becomes a dynamic participant in the cosmic drama, a key that could unlock the secret of the vacuum itself and reveal why the universe is not just expanding, but running away from itself into an ever deeper darkness. Yet for all the exotic possibilities we've explored, from extra dimensions to dark energy, there remains a mystery rooted in one of the most fundamental concepts in all of physics: entropy. This is not a flashy mystery of new forces or hidden dimensions, but a deep thermodynamic puzzle. Entropy, often loosely described as the measure of disorder or randomness in a system, is in a more precise sense a count of the number of ways a system can be arranged. It is the arrow of time, the reason events proceed in one direction and not the other. The universe as a whole has been flying apart and becoming more disordered since the moment of the Big Bang, and its total entropy has been increasing. We can calculate this cosmic entropy budget, and when we do, we find that the cosmic neutrino background holds a surprisingly significant share of it. But is it the share we expect? This entropy mystery asks whether the neutrino sees disorder is exactly what our models predict, or if it reveals a hidden component of the cosmos or a flaw in our understanding of thermodynamics itself. To appreciate the scale of this puzzle, we need to understand where the entropy in the universe actually comes from. The overwhelmingly dominant source of entropy in the cosmos is not planets, stars, or even black holes. It is supermassive black holes. The incredible gravitational chaos within these monsters contributes a staggering amount to the universe's disorder. But in second place, remarkably, is the cosmic microwave background, the afterglow of the Big Bang. Its countless photons, stretched to low energies but unimaginably numerous, represent a huge reservoir of entropy, and following right behind it in a very close third place is the cosmic neutrino background. Given that there are far fewer relic neutrinos than relic photons, about 336 per cubic centimeter, compared to about 410 photons, you might expect their entropy to be much lower. But entropy doesn't just depend on the number of particles, it also depends on their energy and how they can be arranged. The fact that neutrinos are fermions, a different class of particle than the photons, which are bosons, fundamentally changes the calculation of their contribution to the cosmic chaos. This is where the physics gets exquisitely subtle. Fermions, like neutrinos, obey the Pauli exclusion principle. This means that no two identical fermions can occupy the same quantum state. It's the rule that prevents all the electrons in an atom from crashing into the lowest energy level. This restriction actually limits the number of ways fermions can be arranged, which places a cap on how much entropy they can contribute. Photons, being bosons, have no such restriction. Any number of them can pile into the same state. In the dense early universe, this difference was critical. As the universe expanded and cooled, the entropy of both the photon and neutrino seas was effectively frozen in. Our standard models allow us to calculate with great precision what the ratio of their entropies should be today. This prediction is a fundamental check on our entire story of the Big Bang. A serious discrepancy here would be a major problem. if the measured entropy of the neutrino background, or more accurately, the gravitational consequences of that entropy, were significantly different from our prediction, it would suggest that something is missing from our accounting of the early universe. One possibility is that there were additional, unknown types of lightweight particles present during those first crucial seconds. These particles would have contributed their own entropy to the cosmic budget before eventually decaying or otherwise disappearing, leaving the entropy total higher than our neutrino photon model can explain. The entropy of the neutrino background is thus a kind of fossilized audit of the number of particle species present in the universe's first instant. Perhaps even more profound is the potential to challenge thermodynamics itself. Our entire understanding of entropy is based on the assumption of equilibrium, that systems have had time to settle into their most probable states. But the early universe was expanding so rapidly that it may never have been in perfect thermal equilibrium. The neutrino decoupling itself was not an instantaneous switch but a gradual process. If this process happened out of equilibrium, it could have left the neutrino sea with a slightly different entropy value than our equilibrium-based calculations predict. Finding such a signature would be incredible. It would mean that the cosmic neutrino background preserves a record of a non-equilibrium process from the first second of time, offering a unique testing ground for the laws of thermodynamics under the most extreme conditions imaginable. By studying the gravitational influence of this ancient sea of disorder, we are indirectly reading the universe's original ledger of chaos, checking for any entries that don't quite add up. Now we venture into a shadowy realm of cosmic extremes, where the universe's smallest particles meet its most voracious gravitational traps. Primordial black holes represent one of the most intriguing hypothetical entities in all of cosmology. Unlike the stellar mass black holes formed from collapsing stars or the supermassive ones anchoring galaxies, these would be true relics of creation, forged not from dying suns but from the incredible density fluctuations in the very first instance after the Big Bang. They could range in size from smaller than a proton to larger than a star, and their potential existence opens a fascinating new chapter in the story of the cosmic neutrino background, one of violent gravitational encounters and subtle, lasting scars. The formation of these ancient black holes would have been a dramatic event, a gravitational collapse occurring in the searing heat of the universe's first second. As they came into being, they would have been immediately immersed in the dense, hot sea of particles that filled the young cosmos, including the vast number of neutrinos that were still tightly coupled to the primordial plasma. The gravitational pull of even a small black hole is immense, and it would have begun immediately acting on this surrounding neutrino bath. The region of space around a primordial black hole would have become a gravitational well, pulling streams of neutrinos toward it. Some of these neutrinos would have been captured, adding their minuscule mass to the black hole in a process called accretion. But the vast majority, true to their ghostly nature, would have simply had their paths bent or gravitationally lensed by the black hole's presence before continuing on their way. This interaction, happening across the universe wherever these black holes existed, would have created a specific, non-random pattern in the trajectories of the relic neutrinos. This leads to a profound possibility. The gravitational influence of a population of primordial black holes could have left a distinct imprint on the cosmic neutrino background. Instead of a perfectly smooth and uniform sea, the neutrino background would have subtle variations in density, minuscule clumps and deficits corresponding to the locations where black holes either captured neutrinos or scattered them. It would be like a gentle rain falling on a pond. The surface is mostly smooth, but where a raindrop hits, it creates a temporary divot and radiating ripples. Primordial black holes would have been the raindrops in the neutrino sea, and their gravitational ripples would have been frozen in place as the universe expanded. The resulting pattern would be a fossilized map of their distribution, a ghostly image of the universe's first black holes etched onto its oldest particle background. The hunt for this imprint is one of the most creative endeavors in modern cosmology. We cannot see these patterns directly, but we can search for their gravitational consequences. The subtle clumping of neutrinos around the locations of primordial black holes would have created corresponding variations in their gravitational pull. This, in turn, would have influenced how dark matter began to cluster in the early universe, seeding the formation of the first structures in a unique way. If a significant number of primordial black holes exist, they would have acted as natural nucleation points for the growth of galaxies. The large-scale structure of the universe today might therefore contain a hidden statistical signature, an overabundance of certain sized structures or specific correlations in their distribution that points back to this early gravitational sculpting by black holes. Projects like the James Webb Space Telescope, which is peering back at the very first galaxies, could potentially find evidence that they formed earlier or in greater numbers than standard models predict, a hint that primordial black holes were there to give them a gravitational head start. Perhaps the most exciting prospect is that this neutrino black hole interaction could solve two mysteries at once. Primordial black holes are a leading candidate for dark matter, especially if they fall within a specific mass range. If they do make up the dark matter, then their gravitational imprint on the cosmic neutrino background would be universal and significant. By comparing ultra-precise observations of the cosmic web to advanced simulations that include both neutrino physics and populations of primordial black holes, cosmologists could potentially rule in or rule out entire classes of dark matter models. The silent, ancient sea of neutrinos becomes a colossal photographic plate, having recorded the shadowy presence of the universe's first black holes billions of years before the first star ever shone. Finding their faint signature would not only confirm their existence, but could finally reveal the true nature of the invisible matter that holds the cosmos together. Yet, even as we contemplate these gravitational echoes from the dawn of time, we must also consider a far more violent and direct conversation happening in the voids of space, a high-energy interaction that could rip open a new window into the cosmic neutrino sea. Imagine the most powerful particle accelerators in the universe, not built by human hands but forged in the hearts of active galaxies and the cataclysmic deaths of stars. These cosmic engines can blast out neutrinos with energies millions of times greater than anything produced at CERN, particles screaming across the universe at near light speed. Now picture one of these ultra-high-energy neutrinos on a collision course with a particle from the coldest, slowest population in existence, a relic from the cosmic neutrino background. Their meeting would be a spectacular event, a clash of cosmic extremes that could light up the darkness and reveal secrets of both the ancient and the modern universe in a single, brilliant flash. This incredible process is known as a cosmic neutrino cascade, and it operates on a principle of sheer, unimaginable energy. The relic neutrinos from the Big Bang are incredibly lethargic, their energy sapped by 14 billion years of cosmic expansion. But an ultra-high-energy neutrino from a distant blazar or gamma-ray burst carries a phenomenal amount of punch. If these two particles were to collide, the resulting interaction would not be a gentle nudge, it would be a catastrophic annihilation. The immense energy of the incoming particle would be dumped almost instantaneously into the creation of a new particle, most likely a Z boson, the heavy, short-lived carrier of the weak nuclear force. This Z boson would then immediately decay, producing a shower of secondary particles, a cascade of hadrons, leptons, and photons all bursting forth from the point of impact. It's the ultimate cosmic payoff, transforming the silent, invisible passings of two ghosts into a dazzling firework of detectable energy. The beauty of this theoretical phenomenon is that it turns the entire universe into a colossal particle detector. We wouldn't need to build a machine the size of a solar system to catch a relic neutrino. We could instead watch for the brilliant aftermath of its destruction. Our existing neutrino observatories, like the ice cube detector at the South Pole, are already perfectly tuned to detect the faint flashes of Cherenkov radiation produced by high-energy particle showers in the ice. A neutrino cascade event would stand out dramatically in their data, a sudden, immensely energetic burst with a very specific signature pointing back to a patch of seemingly empty space. It would be the telltale sign of a direct hit, a once-in-a-lifetime capture of a particle that has been flying undetected since the first second of time. But the implications reach far beyond just a clever detection method. The rate at which these cascade events occur is exquisitely sensitive to the density of the cosmic neutrino background. If we were to detect them, we could finally perform a direct census, counting the number of relic neutrinos in intergalactic space by measuring how often they get in the way of their high-energy cousins. This would provide the ultimate test for the missing neutrinos paradox, giving us a firm number to either confirm our models or send us back to the drawing board. Furthermore, the energy spectrum of the resulting cascade would be imprinted with information about the mass of the relic neutrino that was hit. Different masses would produce slightly different shower profiles, meaning each cascade event could act as a tiny scale, weighing the ancient neutrino and providing crucial data to finally solve the mass hierarchy conundrum. This creates a symbiotic relationship between the oldest and the most energetic neutrinos. By studying the paths of the ultra-high-energy particles that do reach us unscathed, we can also learn about the obstacles they didn't hit. A deficit of these particles coming from certain directions could map out regions where the cosmic neutrino background is denser, acting as a form of neutrino tomography that charts the distribution of this ancient sea across the cosmos. We are on the cusp of being able to conduct this incredible experiment. As IceCube and next-generation observatories like the proposed IceCube Gen 2 collect more data, they are actively searching their archives for these rare and explosive encounters. Each one would be a Rosetta Stone, a single event that deciphers the properties of both the messenger from a distant catastrophe and the silent, ancient ghost it annihilated, revealing the universe's history written in the language of particle collisions. But this journey to the very edge of physics brings us to a mystery that challenges one of the most sacred principles in all of science, the absolute symmetry of space-time itself. For over a century, Einstein's theory of relativity has been the bedrock of our understanding of the cosmos. At its heart lies Lorentz symmetry, the elegant principle that the laws of physics are exactly the same for all observers, no matter their speed or direction. It's why the speed of light is constant, and it's woven into the very fabric of our most successful theories. But what if this perfect symmetry is not quite perfect? What if, under the most extreme conditions, this foundational rule shows tiny hairline cracks? This is not mere speculation. It's a serious possibility explored by several theories of quantum gravity, and the cosmic neutrino background might be the only witness capable of revealing it. The idea of Lorentz violation is as radical as it gets. It suggests that the vacuum of space itself might have a subtle preferred direction, an underlying graininess that makes one direction in the universe fundamentally different from another. In such a universe, the speed of light might not be perfectly constant for all wavelengths, or different particles could experience space-time in slightly different ways. For most of physics, this symmetry is so fundamental that violating it seems unthinkable. Yet, many attempts to reconcile gravity with quantum mechanics, including string theory and loop quantum gravity, naturally allow for the possibility that Lorentz symmetry might break down at the incredibly small Planck scale. The energy required to see this effect directly is forever beyond our reach, but its consequences might have been magnified and frozen into place in the universe's first second, preserved in the oldest fossil we know. This is where the relic neutrinos become our most sensitive compass. As the earliest free-streaming particles, they have been traveling for nearly 14 billion years. Their immense journey means that even a fantastically tiny violation of Lorentz symmetry would have had ample time to accumulate into a detectable effect. Imagine a violation that causes a neutrino's spin to very slowly precess or wobble as it travels through space. For a single neutrino on a short trip, this effect would be utterly insignificant. But for a sea of neutrinos on a 14 billion-year journey across the cosmos, these tiny wobbles could add up. The spins of the entire cosmic neutrino background could have become collectively aligned with the universe's hypothetical preferred direction, imparting a large-scale polarization to this ancient sea. The entire background would have a faint but coherent spin direction, a ghostly arrow pointing towards a fundamental asymmetry in the architecture of reality. Furthermore, a Lorentz violation could have affected how the neutrinos propagated through the early universe. It might have modified how they interacted with gravity or with each other, altering the specific pattern of the density anisotropies that were imprinted upon them. The statistical signature of these wrinkles, their size, distribution, and correlation, would bear the marks of this fundamental breaking of symmetry. It would be a pattern distinct from that created by inflation alone, a whisper of new physics encoded in the universe's very first structures. While we cannot yet detect these relic neutrinos directly to measure their spin or their faint density patterns, we can hunt for the gravitational consequences of such a profound violation. A polarized neutrino background would exert a directional gravitational pull on the matter in the universe. This wouldn't be a force that pulls equally in all directions. It would have a slight preference, an anisotropy that could subtly influence how galaxies and clusters align with each other over vast distances. This phenomenon, known as intrinsic alignment, is a key target for next-generation sky surveys like the Vera C. Rubin Observatory. By mapping the orientations of billions of galaxies, cosmologists will search for a coherent, universal pattern in how they point, a pattern that has no conventional explanation but would be the telltale fingerprint of a Lorentz-violating neutrino sea. The discovery of such a signal would be more than just a new particle or force. It would be a revolution in our understanding of the fundamental rules of existence. It would mean that the stage upon which the cosmic drama plays out is not the smooth, featureless arena we've always assumed, but has a hidden texture and directionality. The cosmic neutrino background, in its silent, pervasive journey, has been mapping this hidden geometry for billions of years. By learning to read its gravitational influence on the cosmos it helped shape, we might finally glimpse the true and perhaps slightly asymmetric nature of spacetime itself. Yet for all the mysteries we've unraveled, one cosmic question looms larger than almost any other. Why does anything exist at all? We've already explored how neutrinos might have been the engine that created the matter-antimatter asymmetry, but what if the answer is even more bizarre? What if the universe didn't actually choose a side? What if, on the largest scales, matter and antimatter are perfectly balanced, existing in vast, separate domains, and the ghostly sea of cosmic neutrinos is the only thing that can reveal this hidden cosmic architecture? This idea turns our standard story of baryogenesis completely on its head. Instead of a universal imbalance created in the first instant, this theory suggests that the Big Bang produced a perfectly symmetrical soup. But as the universe cooled, it underwent a process akin to a crystal forming from a supercooled liquid. Tiny bubbles of a matter-dominated phase and an antimatter-dominated phase spontaneously began to nucleate and expand. The incredibly rapid inflation of the universe then stretched these bubbles to astronomical sizes, creating immense regions or domains where one type of matter overwhelmingly dominates. In this scenario, our entire observable universe, with all its hundreds of billions of galaxies, might be just one single bubble within a much vaster cosmic foam. Beyond our horizon, there could be domains of space where the roles are reversed, where atoms are made of anti-electrons orbiting antiprotons, and where any hypothetical antimatter astronomers would look out at a universe made of what they call matter. The immediate and obvious question is, if such domains exist, why haven't we seen any evidence of the boundaries? Where matter and antimatter domains meet, annihilation would occur on a spectacular cosmological scale. The border between a matter domain and an antimatter domain would be a sheet of ferocious energy, glowing with intense gamma radiation as particles and their antiparticles met and obliterated each other. Our most sensitive telescopes have scanned the heavens and found no evidence for such titanic walls of fire. This is the strongest argument against the domain hypothesis. However, if the domains are sufficiently larger than the diameter of our observable universe, then we would simply never see a boundary. We would be living comfortably in the middle of our matter bubble, with the nearest antimatter domain so far beyond our horizon that its light, and the light from any annihilation frontier, has not had time to reach us in the 14 billion years since the Big Bang. The universe could be a patchwork quilt, but our patch is so vast we mistake it for the entire blanket. This is where the cosmic neutrino background becomes our only possible window into this grand cosmic structure. Light, the messenger we rely on for almost all astronomy, has a limited range. We cannot see beyond our observable horizon, but neutrinos, especially these primordial ones, are different. They have been traveling since the first second, far longer than the photons of the CMB. Their horizon is larger. If there are antimatter domains beyond our visible universe, the relic neutrinos that have traveled from those regions would carry an indelible signature of their origin. How, through the subtle yet profound difference between neutrinos and antineutrinos, we know that neutrinos oscillate between their different flavors electron, muon, and tau. But a critical discovery is that neutrinos and antineutrinos do not oscillate in exactly the same way. They violate CP symmetry. This means the pattern of oscillations for a beam of neutrinos is measurably different from the pattern for a beam of antineutrinos. Now, imagine a relic antineutrino from a distant antimatter domain journeying for billions of years and finally entering our matter domain. As it travels through our local sea of matter-dominated neutrino background, its oscillation pattern would be subtly but detectably different from that of a regular neutrino. The entire cosmic neutrino background surrounding us would not be a perfectly uniform sea. It could have faint statistical fluctuations, slight anisotropies in its properties that correlate with direction. In certain parts of the sky, the neutrino background might show a tiny statistical excess of particles that behave like they've oscillated through an antimatter environment. It would be the faintest of whispers, a suggestion that the neutrinos arriving from that particular direction have a different cosmic history. Detecting this directly is, with our current technology, a fantasy. We cannot yet distinguish a relic antineutrino from a relic neutrino, let alone map their distribution across the sky. But the gravitational influence of this potentially patterned neutrino sea offers an indirect path. If the neutrino background is not perfectly uniform in its composition, if it has subtle variations in density and pressure because of these underlying matter-antimatter domain boundaries on a super-horizon scale, then this would have influenced how the very first structures formed. The gravitational seeds for galaxies would have been sown with a slight directional preference. The grand cosmic web of dark matter and galaxies that we see today might exhibit very large-scale statistical anomalies, patterns of alignment or clustering that seem to prefer certain axes over others. By mapping the universe in 3 dimensions on the largest possible scales, cosmologists are essentially conducting a search for the gravitational ghost of these domain walls, a fossilized imprint of a cosmos that is fundamentally balanced yet divided. Finding such evidence would be a paradigm shift of epic proportions, revealing that our universe is not just expanding, but is also a vast and intricate mosaic of matter and antimatter, with the oldest particles in existence serving as the only roving ambassadors between these utterly alien realms. Yet after contemplating such vast cosmic structures, we are drawn inward to a mystery that lies at the very heart of reality's nature. the fragile, elusive boundary between the quantum world and the world we see. In our daily lives, we experience a universe that is definite and concrete. A chair is in one place, not in a superposition of many places. This transition from the fuzzy, probabilistic realm of quantum mechanics to the definite, classical world we perceive is one of the deepest puzzles in all of physics, a process known as quantum decoherence. And incredibly, the universe's oldest particle C might be the one place we can finally observe this transition happening on the grandest possible scale. To grasp why this is so profound, we need to understand the core strangeness of the quantum world. At the subatomic level, particles don't have definite properties until they are measured. An electron can be in a superposition, meaning it is spinning both clockwise and counterclockwise at the same time. A neutrino can be a mixture of all three flavors, electron, muon, and tau, all at once. This is not a lack of knowledge, it is a fundamental description of its state. So why don't we see these superpositions in our macroscopic world? Why doesn't a baseball exist in two places at once? The prevailing theory is decoherence, the interaction of a quantum system with its messy, complex environment. Every time a particle bumps into another, or even just feels the gravitational pull of distant stars, its delicate quantum phase relationships get scrambled, effectively erasing the superposition and forcing it to choose a single classical state. This process is usually incredibly fast, happening in fractions of a second in a laboratory. We've never been able to watch it unfold slowly because we can't isolate something from its environment for long enough. This is where the cosmic neutrino background presents a scenario unlike any other. Imagine a single relic neutrino set free in the first second of the universe. It has been traveling almost completely alone for nearly 14 billion years. Its environment is the nearest thing to a perfect vacuum that exists, the immense, nearly empty expanse of intergalactic space. It might interact gravitationally with the large-scale structure of the universe, but these interactions are incredibly weak and incredibly rare. This particle has been almost perfectly isolated from its environment for an almost unimaginable duration. This raises a spectacular possibility. Could such a neutrino have maintained its quantum coherence over this vast cosmological distance? Could it still be in a true quantum superposition of states, a living fossil from the quantum era of the universe? If so, the entire cosmic neutrino background wouldn't just be a sea of particles. It would be the largest-scale quantum system in existence, a universe-sized experiment in superposition. The implications of this are staggering. If we could find a way to measure the coherence of these ancient neutrinos, we could finally watch decoherence happen not in nanoseconds but over billions of years. It would be the ultimate slow-motion replay of the quantum to classical transition. This would allow us to test the very limits of quantum mechanics itself. Do quantum superpositions inevitably collapse over time, even in perfect isolation? This is a question some interpretations of quantum mechanics, like the spontaneous collapse models, answer with a yes. They propose a fundamental mechanism that causes superpositions to break down after a certain time, a process completely independent of environmental interaction. The cosmic neutrino background is the only laboratory where this could be tested. A neutrino that has been traveling for 14 billion years would be the ultimate test subject. If we found evidence that its superposition had collapsed, it would provide powerful support for these radical theories. If we found evidence that it was still coherent, it would be a triumph for the standard, yet bizarre, interpretation of quantum theory. But how could we possibly measure the quantum state of a particle we can't even directly detect? The answer, once again, lies in the gravitational ledger. A neutrino in a quantum superposition has a different effective gravitational field than a neutrino in a definite state. The bizarre rules of quantum mechanics suggest that the energy and mass in a superposition are distributed differently, which would subtly alter how it warps the spacetime around it. If a significant portion of the cosmic neutrino background were still coherent, its collective gravitational influence on the formation of the cosmic web would be unique. It would have impeded the growth of the smallest structures in a different way than a sea of classical particles would have, by creating exquisitely detailed computer simulations of the universe's evolution that include both possibilities. A classical neutrino background versus a quantum-coherent one. Cosmologists can look for a telltale signature in the distribution of galaxies we see today. The pattern of tiny dwarf galaxies and the intricate filaments of the cosmic web could hold the faint imprint of a sea of particles that never quite chose a definite state, a ghostly reminder that the quantum world might be far larger and more persistent than we ever dreamed. After contemplating the profound quantum nature of these ancient particles, we arrive at our final and perhaps most humbling mystery. It is a challenge that brings us full circle, back to the very reason this ghostly sea remains so enigmatic, our fundamental inability to directly perceive it. For all our theoretical brilliance and cosmic inference, the ultimate prize in neutrino physics would be to finally capture a single, definitive signal from the cosmic neutrino background itself. This is the ultimate detection challenge, a monumental technological hurdle that pushes the very limits of human ingenuity and may require us to build the most sensitive machines the world has ever seen. The core of the problem is almost absurdly simple, yet insurmountably difficult. These relic neutrinos are unimaginably cold and slow, with energies millions of times weaker than the neutrinos we already struggle to detect from the sun or from nuclear reactors. Their signal is not just faint, it is buried beneath an avalanche of noise from every other process in the universe. To detect them, we need to invent an entirely new form of astronomy, one that can isolate this faintest of whispers from the cosmic cacophony. The first and perhaps most elegant approach is not to look for the neutrinos themselves, but for the tiny, telltale recoil they impart when they bump into another particle. This is the principle behind the Ptolemy project, a bold proposal that aims to use a solid surface coated with an ultra-pure layer of radioactive tritium. The idea is exquisitely clever. When a relic neutrino scatters off a tritium nucleus, it would transfer a minuscule amount of energy, just enough to slightly change the energy spectrum of the electrons emitted during the tritium's natural beta decay. By measuring the energies of billions of these decay electrons with phenomenal precision, scientists hope to see a tiny distortion in the spectrum, a specific bump or edge that can only be caused by the interaction with the ancient neutrino sea. It's like trying to hear a single, specific pin drop in a thunderstorm by analyzing the precise sound wave of every raindrop. The technical challenges are staggering, requiring temperatures near absolute zero, unprecedented vacuum conditions, and a level of background radiation suppression that borders on the impossible. Yet the potential payoff, a direct laboratory-based measurement of the universe's oldest particles, makes it a pursuit of epic proportions, but tritium decay is just one path. Other visionaries are looking even further ahead, designing neutrino observatories that belong in the pages of science fiction. Imagine a detector so massive it uses an entire planet as its instrument. One futuristic concept involves placing ultra-sensitive seismic sensors deep within the moon. The theory is that the constant, gentle rain of cosmic neutrinos, including the relic background, would very occasionally interact with the lunar rock, generating minuscule vibrations. By listening to the moon's interior with a global network of these supersensitive ears, we might be able to pick out the unique seismic signature of a relic neutrino interaction from the background rumble of moonquakes and meteorite impacts. It sounds like fantasy, but it underscores the scale of the challenge. We are contemplating interplanetary experiments to catch a particle from the first second of time. Perhaps the most promising long-term avenue lies not in detecting the neutrinos one by one, but in capturing their collective gravitational influence in a way we never have before. The next generation of cosmological surveys, like the Legacy Survey of Space and Time at the Vera C, Rubin Observatory and the Euclid Space Telescope, will map the universe's large-scale structure in such exquisite detail that we will effectively be creating a three-dimensional movie of cosmic evolution. Within this immense dataset, the gravitational footprints of the cosmic neutrino background will be writ large. By comparing these ultra-precise observations to increasingly sophisticated supercomputer simulations, we will be able to measure the properties of the neutrino sea with a precision that rivals any direct detection experiment. We will weigh it, take its temperature, and map its distribution all through its ghostly tug on the cosmos it helped to shape. This indirect method may well provide the first unambiguous confirmation of its specific properties, acting as a guide for the engineers building the machines that will one day capture it directly. The quest to detect the cosmic neutrino background is more than a technical puzzle. It is a testament to human curiosity. It represents our unwavering desire to touch the untouchable, to see the unseeable, and to connect directly with the moment of our universe's birth. Each proposed experiment, from the tabletop precision of Ptolemy to the planetary scale of a lunar observatory, is a step toward closing the circle on our cosmic story. While the relic neutrinos themselves may be silent and ghostly, our pursuit of them is a loud and brilliant declaration of our need to understand where we came from and to finally listen to the faintest echo of creation itself. And so we reach the end of our journey through 25 of the universe's most profound secrets, all held within the silent, ghostly sea of the cosmic neutrino background. These are not merely academic curiosities. They represent the absolute frontier of human knowledge, the bleeding edge where cosmology and particle physics collide. Each mystery we've explored, from the neutrino's impossible lightness and its potential decay to its role in the matter-antimatter asymmetry and its whispers of quantum gravity, is a direct challenge to our most fundamental theories. This ancient fossil is more than a snapshot. It is an active interrogation of the standard model of general relativity and of our very understanding of what reality is. It pushes us to consider extra dimensions, cosmic strings, and the possibility that the constants of nature might not be so constant after all. This is where textbook science ends and the true exploration begins. The cosmic neutrino background stands as one of the last great uncharted territories in our cosmic map. We have brilliantly illuminated the era of the cosmic microwave background, and we are rapidly unraveling the history of galaxies and stars. But the first second, that crucial, frenetic moment when the universe's destiny was truly forged, remains shrouded in mystery. This relic sea is our only direct link to that epoch, a messenger from a time when the forces of nature were unifying and the seeds for everything we see were being sown. It is the final missing piece in our standard model of cosmology, and until we can directly measure it, our picture of the universe is frustratingly incomplete. We are like cartographers trying to map a continent we can only sense by the subtle way it bends the light from distant stars. Contemplating the solutions to these puzzles is to contemplate a series of scientific revolutions. Discovering that neutrinos have decayed would shatter the standard model. Measuring their mass hierarchy would point us toward the correct grand unified theory. Finding evidence that they interacted with dark matter or were influenced by cosmic strings would open portals to entirely new realms of physics. Each answer would not just solve a single mystery, it would unleash a cascade of understanding, fundamentally rewriting chapters in our physics textbooks and forcing us to see the cosmos in a completely new light. The potential is staggering. We could finally understand why we live in a universe of matter, what dark matter truly is, and how the bizarre quantum world of the very small connects to the vast cosmic arena. This pursuit is a powerful testament to human curiosity and ingenuity. We are building detectors deep underground in Antarctic ice and even planning them for the moon, all to catch a glimpse of a particle that barely exists. We are writing complex algorithms to scour the sky for the gravitational ghosts of these ancient neutrinos, using the universe itself as our laboratory. It is a grand, collaborative effort that stretches across disciplines and decades, a shared desire to listen to the faintest echo of creation. So the next time you look up at the night sky, remember that you are not just looking at stars and galaxies. You are looking at a cosmos filled with billions of ghostly particles from the first second of time, each one holding a secret that could change everything we know about reality. The story of the universe is still being written, and we are on the verge of reading its very first page.